Hello everyone, so here is the second video of this review for function unit part 2. And so now we're going to focus on piecewise functions, and in your review you were given those two piecewise functions and you had to evaluate them at specific values. So let's try. If I'm looking at g of 8, so I'm looking to my g function here is my piecewise function g, and I want to evaluate it at x equals 8. So the first job is to figure out in which section of my equation am I going to input a value of 8. So is 8 less than 0? No. Is 8 between 2 and 8 but not equal to? Well, no, right? So 8 will be equal to 8, so this is the section where that would fit in the domain. Therefore, I will use this equation right here. And so it will be square root of 8 plus 17. And 17 plus 8 will be 25, so that will be a square root of 25, which is equal to 5. So that will be this answer. Then the next one is h of -1, so I'm going to my h piecewise function here, and I need to figure out in which of those three pieces or branches or equation I will enter my input of -1. So look at your domain for each little section of the piecewise, and you ask yourself, is -1 less than or equal to -10? Well, no. Is -1 between -10 and 10? Yes. So this is where I'm going to input my -1, so that's the section I will use. So this is going to be -1 cubed minus -1. Well, -1 cubed is just going to be a -1. Minus minus becomes plus, and -1 plus 1 is 0. So that will be this answer. Then you're going to do h of 10, and h is this function. So where in my piecewise am I going to plug in my input of 10? So is 10 less than or equal to -10? No. And then is 10 between -10 and 10 but or equal to 10? So yes, definitely, right? This 10 will be or equal to 10 here, so that's the section where I want to plug it in. Not here, because this one doesn't say or equal to. So that will be again in the section that should be a positive 10 cubed minus 10, right? 10 cubed minus 10. And so 10 cubed is 1,000, and 1,000 minus 10 will be, 990. And then finally, g of 1. So I'm going to my g piecewise function, and I want to know where is my input of 1 fitting. So let's look. So is 1 less than or equal to 0? No, so we can't put it there. Is 1 between 2 and 8? Well, no, right? And 1 is not greater than 8 either. So 1 really doesn't fit anywhere in my domain. Therefore, 1 is not defined in my g function, so undefined. All right, so that was for this one. I'm going to come back here, and I'm going to, so we have to graph these piecewise functions. And if I need to graph this, I'm going to look at my parent function, and that's a quadratic. So I know that my quadratic parent function will be a parabola right there with the vertex at the origin. And then I'm looking, I say, okay, my parabola has been moved 3. When you see a plus on the inside with the x, that means you go opposite of what you think. So you go toward the negative side, so on left 3, down 4, but we have a vertical stretch. Don't forget about that stretch, a vertical stretch of 2. So let's go first. Left 3, so 1, 2, 3. We're here. We're going down 4, 1, 2, 3, 4. So that's where the vertex is. And now, instead of going up 1 over 1, because I have a vertical stretch of 2, I'm going to go up 2 over 1. Technically, the parent function will be the next one up 3 over 1, because remember, we do the odd numbers. So here, since I multiply by 2, I will go up 6. So 2, 4, 6, and then over 1. So it makes my parabola very skinny. And before I draw it, I now look at the domain, and I want that parabola for all the x's less than -2. So my -2 will be right there. That's where negative 2 is, right? Negative 2 is right here. So I only want the section that's on that side of negative 2. So that's where I'm going to draw it. As good as I can, right? It's not perfect, but as good as I can. And then I have to ask myself, do I want that last point here to be closed or open? And it's not or equal to, so I want a bubble here. So I'm going to do a little bubble right there, an open dot, right? And I'm going to erase that point I drew just to help me, but I didn't need. So this is the section for the parabola. And then I go to this part. And this one is just a linear equation. And it's going to be negative 3/4 x plus 2. And it starts where x is greater than 1. So I'm going to take that one and I'm going to plug it in here for x, see what I get. So that would be, let's do it up here. So I would have negative 3/4 and then times 1 and then plus 2. So I have a negative 3/4 plus 2 over 1 because I need a common denominator, right, to be able to add fractions. So I need to multiply by 4, top and bottom, because multiplying by 4 over 4 is just like multiplying by 1, which doesn't change anything to our fraction. And so that would be negative 3 plus 2 times 4 is 8. And now I have a common denominator at the bottom, so I can just write it once. Negative 3 plus 8, that would be 5, and 5 over 4 is the same thing as 1.25. Okay, so that's where my point will be. My point will be for an x of 1, the output will be 1.25. So for an x of positive 1, the output is 1.25, so about there, and it is an open circle, so put a circle there. And then my slope is down 3 over 4, right? So down 3, 1, 2, 3 over 1, 2, 3, 4, so right there. And then I kind of just draw my line and put an arrow at the end. So that will be my piecewise function here. Let me erase that. There we go. For 14, we are given the equation, the graph, and we actually have to write the equation, okay? So let's do that. So we need 1, 2, 3, 4 pieces, right? My first piece is an upside-down parabola, so I know that the parent function of a parabola would just be y equals x squared, centered here. So this vertex has been moved way up there. So we're going to go 1, 2, 3 to the right. Sorry, that's the left, not the right. So it will be x plus 3, because inside it's opposite of what you see, squared. And then I'm going to go up 1, 2, 3. So plus 3 to go up. And then the whole parabola is upside down, so I need a reflection over the x-axis. So there it goes. And then the last point, or the point most to the right I have, is at negative 2, and it's a closed dot, so I want an or equal to at negative 2. So that's for all the x's that are less than or equal to negative 2. Less than because they're on the left, right? That parabola is on the left of that point, negative 2. Then my next section is at constant, and a constant is just going to be a y value, a number, and it's negative 1 here, right? So at negative 1, I'm going to have a horizontal section, and that's from negative 2 all the way to 1, but not or equal to on either end. So x is going to be between negative 2 and positive 1, but not or equal to. Then I have a floating point right there, so that would just be a y value for one specific x value. So my y will be 3 when x equals 1. So y is 3 when x equals 1. And finally, I have this little absolute value piece here. And the absolute value parent function will be sitting right here at the origin. So it has been moved 1, 2, 3 to the right. So that will be absolute value of x minus 3, because this time I'm going right, and opposite of what I see, so toward the positive side of the values, you're going to have a minus here. Then it's been moved up by 1, so plus 1. And then finally, we're going to have that little reflection because it's upside down. So I put a negative in the front, and let me move that down a little. Here we go. And that will be for all the x's that are greater than 1, right? Because we have an arrow at the end here. So for all x's greater than 1, but not or equal to, because it's an open circle. There we go. Number 15 was part of your review here, so let's just briefly look at it. Here it just says, is this function continuous? And we have to wonder, continuous. Well, that's continuous by itself. That's continuous by itself. But are those two pieces connected on the graph? Because you see how when you have a piecewise function, sometimes the pieces are not connected, right? And here it's easy to see because the x's are not the same. But notice here how at -2, the function, the two pieces are not connected, so the function is not continuous there. Yet when you're looking at the domain here on the side, you would think they are because one starts where the other one stops, right? But they're not starting and stopping at the same y value, even though it's the same x. So that's what you have to check here. Those are the same x's, but will they give you the same y here? So check it out by just plugging in. So we're going to plug in a -3 in this quadratic to see what we get, right? So we have -3 squared plus 2 times -3 plus 11. And that will be equal to -3 squared is 9. And then we have a negative in the front, so -9. 2 times -3 is -6 plus 11. -9 minus 6, that's -15, and -15 plus 11, that will be -4. Okay, so we're at -4. So now we're going to check by plugging in a -3 in this section to see if we end up with the same y value. So we're going to put -3 here, so 2 times -3 plus 2. -3 plus 2, 2 times -3 is -6 plus 2, that will be -4. And because those two are the same y value for the same x's, that means that this function is continuous. So yes, continuous at -3. And continuous here because that's a parabola, continuous here. So continuous everywhere. There we go. That's it for this one. Okay, I want to switch a little bit. I want to do some average rate of change. Or do we need to do that first? Let's do that first. Let's get to finish those. Okay, let's finish this one first. Okay, so your other review here. We were only doing selected numbers, right? So number 2, vertical reflection. Actually, I didn't want this one as a horizontal stretch of 4. So we're going to just ignore number 2 for now. We're going to go to 3. We have an equation. The parent function is y equals x squared. And it sees that the parent function is very, very lightly drawn here. And you want to write the equation of the translation here. So how has it been translated? 1, 2, 3, 4 to the right. So it will be x minus 4 because we're going right and the parent function is quadratic, so square that. Then it's been moved up 1, 2, 3, 4, 5, so plus 5. It is reflected, so we're going to have a negative, but the parent function goes up 1 over 1 and then up 3 over 1. But this one goes down 2 over, no, actually it goes down 3 over 1 until I hit the next. See, if I want to go over 1, to go to the curve again on a corner, I'll actually have to go down 3. So this one will be down 3 over 1 instead of 1. So I need a 3 here. So it's been a vertical stretch of 3. Well, that's not a nice 3 I drew there, but I'm sure you can read it. Alright, then I go here and I want to determine if this function is... No, we don't want to do that. Where am I going? 5. 6. I want to go to 6. Okay, we have two functions given to us, and we want to do 5 plus, g plus f of 4. Well, that's just saying that you want g of 4 plus f of 4. It's a shortcut so that we write 4 only once, right? Instead of writing it twice like that. It's just a shortcut of way of writing this same thing. So g of 4, go to your g, find where x equals 4, your y will be 8. So that will be equal to 8 plus, because we're adding, f of 4. Go to your f function, find where your x is 4, and the y value will be 6. And 8 plus 6 will be 14. So that will be your answer here. Now that's a composition, not a multiplication, right? That little open circle means composition. So you're going to plug in a 0 into g first. So we want to find g of 0 first. Go to g, when x is 0, that will be a negative 2. So then I take that negative 2, and I'm going to now take negative 2 and put it into my f function. So f is here, when x equals negative 2, the y value is 9. So that will be equal to 9. There we go. Then I am going to, okay, here we want to subtract h minus g. So we have three functions given to us up here, and we're going to do some operations with them, and I want to subtract h and g. So we do the h first, right? So it will be 5 minus 3x minus the g function, so minus 3x squared minus 4x. And recall that we said when we're subtracting here, we just distribute that negative, and the first stays the same. So we have a 5 minus 3x minus 3x squared. Negative negative becomes plus 4x. Now we just put our like terms together by starting with the highest exponent. Keep the sign with the term, so negative stays with 3x squared. So negative 3x squared. Then we have a negative 3x and a positive 4x. That will go to a 1x, and then the plus 5 there. So that will be this answer right here. Now we need to figure out the domain. So the domain of this here, well, that's a quadratic. So the domain here will be all real numbers. Quadratics have no restrictions in the domain, so it's just all real numbers. Okay, number 8. This is a composition of function. So the first thing you do is always start with the inside here. So we want g of negative 2. So go to your g function. So I'm going to do that down here. And I want to plug in a negative 2 in g. So that will be 3 times negative 2 squared minus 4 times negative 2. Negative 2 squared is a positive 4. 4 times 3 is 12. Negative 4 times negative 2 is positive 8, and so that will be 20. So now I have a 20 that's going to be replacing my g of negative 2. So now I want f of 20. So go to your f function, and now we're going to put a 20 in here. Well, that's going to be a little messier, because that will then be a 20 squared minus 1, and in the denominator we have a square root of 2 times 20 plus 9. And at this point you will be welcome to use your calculator. 20 squared will be 400, and 400 minus 1 is 399, over 2 times 20 is 40, 40 plus 9 is 49, and the square root of 49 is 7. So we'll have 399 over 7. And this is going to, let's see. Okay, so I'll show you that in my calculator here. 399 divided by 7, right? And I get 57. And so that will just be equal to 57. So f of g of negative 2 is equal to 57. For number 9, we're dividing the g function divided by the h function, so that will just be 3x squared minus 4x divided by 5 minus 3x. And that will be it, right? I'm going to leave it like that as a rational function, but the domain of a rational, remember, That's one of our two troublemaker here, because now we have a denominator and we cannot let that go to 0. So what x number would make that whole thing go to 0? So let's check it out. 5 minus 3x. Which x would make that go to 0? So you're adding 3x to both sides and divide by 3. So 5 over 3 would make that whole thing go to 0. So the domain will be all real number except for that number. So from negative infinity to 5 over 3, not including it, so a parenthesis, jump over it, start on the other side of it, and go to infinity. Okay? Alright, here we're adding, so you're going to do g of 4 plus h of 4. Alright, so g of 4, so you're going to plug in a 4 here and here. So that will be equal to 3 times 4 squared minus 4 times 4. And then we're going to add h of 4. So h of 4, that will be plugging in a 4 in my h function here. So plus 5 minus 3 times 4. Right? So this right here is my g of 4, that's my g function, and this right here is my h of 4, that's my h function. Now I just simplify, compute that. So 4 squared is 16, and 16 times 3 is 48. So I have 48 minus 4 times 4, which is 16. And then I have plus 3 times 4 is 12, and 5 minus 12 will be negative 7. So actually I'm going to change that already. So 5 minus 12 is negative 7, okay. And then I have 48 minus 16 will be 32. And 32 minus 7 will be 25. Okay, and you could absolutely do that in your calculator, no problem. F, now there is nothing in between, so that's assumed to be a multiplication. So really what we want here is f of 8 times g of 8. That's a multiplication, not a composition. So you're going to take your 8, put it in your f function, so that will be 8 squared minus 1 divided by the square root of 2 times 8 plus 9, and then times g of 8, so plug in an 8 here, so times 3 times 8 squared minus 4 times 8. Okay, for the sake of time, we're going to use our calculator here. And my calculator's battery is almost dead, so let's make sure we do it quick. So I'm going to have my 8 squared minus 1 divided by the square root of 2 times 8 plus 9, and then that whole thing is going to be multiplied by 3 times 8 squared minus 4 times 8. Okay, just take a second or two to quickly check that you didn't type anything wrong, to make sure your answer is going to be what you really wanted, and that will be 2016. Okay. And finally, number 12 here, that's a composition, so that's where you're going to compose. So this just really says g of h of x, right? Meaning your h function becomes the input of the g function. So this function becomes the x for the g function. So both of those x's are going to be replaced by 5 minus 3x. Okay, so that would be 3 times my new x, which is 5 minus 3x, minus, oh sorry, and that should be squared, minus 4 times my new x, which is 5 minus 3x. At this point, I would have to simplify, so you have to fold that out, right? You have to distribute, expand that binomial. So 3, and I'm going to expand it, so 5 times 5 is 25. 5 times negative 3x is negative 15x, and another negative 15x will be negative 30x, and then negative 3x squared will be a positive 9x squared. All of that, so here I'm going to distribute the negative 4, so that will be a negative 20, and negative becomes positive 12x. Okay, let's keep going. So that's going to be equal to, multiply everything by 3 here, so that will be 75. That'll be minus 90x plus 27x squared minus 20 plus 12x. And then finally, let's put all those like terms together, and let's start with the highest exponents. So the square comes first, so we have a 27x squared, to be 12. And then we have negative 90 plus 12, that will be 90 minus 10, 80, and minus 2, right? So it'd be a negative 78x, and then 75 minus 20 will be a positive 55. So that will be your answer. And then the domain of that answer, well, really, the domain will be all real numbers, because that's a quadratic, right? So parabolas have all real numbers as domain, so all real numbers. Okay, here it's about inverse functions, so it's our quick little review on inverse functions. And I think we're going to stop the video probably on this one. Okay, so we have to graph f. So here is my function f. So notice that my parent function used to be a square root of x, but this and this you have to be very careful, because see how your x has a negative in front, and we've talked about that and how that would mean that really we're going to have to switch that around, factor out that negative, and that is really x minus 3 and then plus 2. And why do I want to write it this way? Because now I know I'm going to the right 3 and I have a reflection. Horizontal reflection means this way, right, over the y-axis. So I needed to do that, because when it's written like that, you know, not in standard form, I don't really know where I'm moving and what's reflected and what's not. So you're factoring out a negative out of those two. Factoring out a negative out of 3 will become a negative 3, and factoring out a negative out of negative x will make it a positive x, and the negative you factored out of both of them just sneaks in the front there, in front of a parenthesis, okay? So that's all I've been doing, and if you're not convinced, redistribute that negative and you will see you will get back there, right? But you want it in that form so that you see exactly where you're moving, left or right, and then what's the reflection, okay? So here we go. Moving to the right by 3, so here is the origin. We're going 1, 2, 3 to the right, and then I'm going to go up 2, so there is my new vertex here, but then I'm reflecting, so instead of going toward the right, I'm going to go toward the left, so it's going to be up 1 over 1, and then 1, 2, 3 over 1, and so here is my function, my graph, okay? So once I graphed it, I have to verify that f is a one-to-one function. Well, this is a one-to-one because it passes the vertical and the horizontal line test. So I'm going to say one-to-one. Then I need to find the inverse, right? And it's, by the way, it's a one-to-one for what I just said, right? It passes both horizontal and vertical line test. Now we need to find f inverse, and then we have to graph it. So if this is my f function, and I'm going to actually use this one, I'm going to replace the y or the f by an x, and the old x is going to become my new y. And now I'm going to isolate y. So the first thing I need to do is what's outside goes first. So subtract 2. And then I need to get rid of that square root, right? And to undo a square root, we're squaring, but what we do on one side of equal, we have to do to the other. And so I'm going to have an x minus 2 quantity squared is equal to that negative, don't forget it, and then y minus 3. I need to divide by a negative, so that's going to come across there. So negative x minus 2 quantity squared is equal to y minus 3. And then finally now I can add that 3 to both sides. So I would have that my f inverse, and I can use function notation because I decided that it was a one-to-one. Therefore the inverse is also a function. So we can use function notation. So f inverse is going to be equal to negative square root of, oh, sorry. Negative parentheses, so it will be x minus 2 quantity squared, and then I move that 3 across, so plus 3. So that's my inverse function right there. And I'm going to graph it using a different color. So from the vertex, I'm going to go right 2, up 3, so right 2, 1, 2, 3, so that will be the point right there. And then it's a reflection over the x-axis, right? So it'd be down 1 over 1, then down 3 over 1, and so that would be my inverse. And all of that has to be symmetrical over the line y equals x, so I'm going to kind of sketch that. So this is my symmetry, right? Line y equals x, and sure enough, my blue curve and my orange curve are going to be symmetrical over that line, so I know I'm good to go. Okay, so we graph the inverse, we graph the line y equals x, I just did in green, and then we have to state domain range for both f and f inverse. So for f first. So the domain will be most to the left to most to the right. Well, I have an arrow on that end, so I'm going to keep going. So to infinity, negative infinity, sorry. And the first point is this one, and that will be for an x of 3, so that's bracket because it's closed dot. And then the range of that f of x will be the lowest y to the highest. Well, that's going to keep going out and up, so no restriction. The lowest one is a y of 2, so including it, and then going to infinity. And if we recall, the domain of the inverse is the range of the function, so that becomes 2 to infinity. And if you're checking now your orange graph, that will be the left point is 2, and then we're going to keep going to infinity, so that matches perfectly. And then the range of the function inverse is actually the range of the original function, so negative infinity to 3, and that also matches because my highest point is 3 and it goes down to negative infinity. All right, I'm going to stop here. That's a long enough video, it's 33 minutes.